In this video, we're looking at what is the relationship between the put call and the forward agreement, which is called put call parity. What we're thinking about is, can we synthetically create a forward agreement using a put and a call? So let's begin by looking at the forward agreement and reminding ourselves about the shape of the payoff line. So here we're looking from the buyer's view. We know that the forward agreement has a price at which the transaction takes place is called the forward price. When the market price exceeds the forward price, the buyer is making money. Corresponding, the writer is losing, or the seller is losing money. When the price goes below the forward price, the buyer is losing money. So focusing on the buyer's view, when price is above the market price, he has a gain. When the price is below the market price, there's a loss. And there's no investment in a forward agreement. You simply receive or pay depending on how circumstances change. Let's look at the buyer and the writer's view on an option. If we look at the call option, the black line in both cases for the call and the put is the intrinsic value out of the money. Where that black line reaches the red and green is at the money, and then finally red and green will be in the money. So let's start with the call option. The buyer of the call, when the price goes above the strike price, the green line represents his gains. The buyer is making money. Simultaneously, the writer is losing money because the buyer's gain is the writer's loss. Looking at the put, when the price drops below the strike price, the buyer of the put is making money, the green. The writer of the put is losing money. So that what we're looking at in this case is 4 lines, but they're all put into a graph. So let's just focus on, if we did the buyer of the call, the intrinsic value line would be the black line becoming the green line. The writer of the call would be the black line becoming the red line. If we turn to the put, the buyer of the put would be the black line becoming the green line. The writer of the put would be the black line becoming the red line. Going back to the forward, we see that the red line is rising as you move to the right. The green line is also rising as you move to the right. Going back to the options, the way we would get rising as you move to the right would be the right of put. If we write a put, the red line is rising to the right, to the intrinsic value line or out of the money line. If we look at the call, the green line is going up in the same direction. You could kind of mentally picture the two little graphs getting together, and you would have a red line connecting to a green line. So we know that write a put and buy a call will produce something that looks like a forward agreement. So let's pursue that a little more. The black line is the forward agreement. We see it's a continuous black line. Now if we look at B and C, C is writing a put, B is buying a call, but it's not a continuous line because the strike prices are not the same. So we now know something else. We need to have the strike prices to be the same. Now we look at E and D. E and D, the strike prices are the same. We get a continuous line. The only problem is it's to the right of A, which means the strike price of E and D is higher than the price in the forward contract called the forward price. So the only way we're going to shift E and D over to be right on top of A would be to make the strike price of the put and call equal the forward price, and that's what we call put-call parity. Let's do it again, but this time with a set of numbers. So if we look over here, I have 3 represented synthetic forward lines, 1, 2, and 3. The market price is 15%, or $15. We're going to write a put and use the money to buy a call. So the market price is 15, strike is 15.20. The put generates $1.14, but that's not enough money to buy the call at $1.24. We're short 10 cents. That is a synthetic forward, but not exactly a forward agreement because we have to put in 10 cents. If we go to 15.50, we're going to have a put price of $1.30, which exceeds the call price of $1.11. We have 19 cents extra. Again, it looks like a forward agreement, but we have extra money coming in. This is not a true synthetic forward agreement. So we look at the graph. 1 is one extreme to the left, 2 is the other extreme. Let's try something in the middle, 3. So 3 is a strike price of $15.30. Put price is $1.20, call price is $1.20. So they are exactly equal to each other, and so we now know that the put can be used to buy the call. we've now created a synthetic forward agreement involving no input of money, no extra money left over, so the 15.30 has to be the forward price. The problem with number one is the strike is below the forward price, allowing the call to be more valuable than the put. In the second one, the strike price is higher than the put price, and now the put is worth more than the call. So we have to go with the idea that for parity to take place, for the put and the call to synthetically make a forward, the forward price and the strike price have to be the same. So this is called put-call parity. If we come down to the next page, next slide, I'm going to focus on the formula under the word put-call price parity. On the left-hand side in brackets is call price minus put price. On the right-hand side is today's market price minus the present value of the strike. So let's again return to call price and put price. If we set them equal, call price minus put price is 0. The left-hand side of the equation is 0. How do we get the right side to be 0? We have today's market price minus the present value of the strike. How can the present value of the strike price be the same as today's price? The strike price would have to be the future value of today's price. Future's value of today's price is called the forward price. So if we drop down one line, if the strike price equals the forward price, that's equal to the future value of today's price. If we present value the future value of today's price, we get back to today's price. So we now have confirmed the put-call parity relationship. I'm going to refer to today's stock price minus the present value of the strike price as simply the price difference. So if we look at the call price, we can price a call based on a put, or we can price a put based on a call. Cleaning this up so we're only on one page of formulas. The call price is going to be equal to the put price plus that price differential. The put is going to be the call minus the price differential. So once I know one of the two options, I can find the price of the other. Once I know any three of the variables, I can find the fourth. That's also a possibility. So let's take a look at a table. I've got some blank yellow spaces that we are to calculate. So in the first row, we need the put price. So the put price is going to be the call minus the price differential. The price differential is 15 minus 14.70, which is 30 cents. So the put has to be $1.30 less 30 cents, which would be $1. If we look at 2 and 3, in both cases, we're looking for the call price. We look at the top formula. Call price is the put plus the price differential. So number 2, the price differential is 20 minus 20.40, which is 40 cent negative. $1 minus 40 is 60 cents, so the call is going to be cheaper than the put, and it'll be 60 cents. If we look at the next one, the stock price is greater than the present value of the strike by 20 cents, so the call is going to be greater than the put price by 20 cents, so it'll be $1.65. So if the differential is positive, the call is greater than the put. If the differential is negative, the call is less than the put. The last one, the put and call are the same price, so the present value of the strike has to equal today's price, which is $25. On the next slide is a practice problem. After the practice problem comes the solution to it. So I'd like you to fill in these boxes, pause the video, do the calculations, and when you're done with the calculations, compare it with the next slide. Here is the next slide. So in the first one, the put is going to be 90 cents. We see that because the call minus the differential of 30 cents is 90 cents. In the case of the call, it's going to be put plus the differential. If we look at number 2, the differential is negative, so 60 cents plus a negative 40 cents gives us a call of 20. The $1.20 put plus the differential of 20 cents for number 3 makes the call $1.40. And the last one, for the two options that are the same price, the stock price and the present value of strike price have to be the same. And that brings put-call parity to a solution and to a completion. And I would like you to review this before you go into how to use the Black-Scholes model to price options. That's another video called Calculating the Option Price Using the Black-Scholes model.